Probably the example we talked in our exam 2, where I asked you to find a binomial on one tail, and I also only asked you to do, n was 10, and to do more than 2, or at least 2. And some people did it all the way to from 2 and 3 and 4 and 5. So now think about a situation where it's not feasible to do either way. Like an example right here, 50% of adults say that they prefer coffee over tea in the morning, and you randomly select 60 of them and ask them if they prefer coffee or tea in the morning. Well, they'll probably do that at least 20. Okay, the key point here is that at least 20, when there's 60, you either have to do 41 of these. You have to do at least 20, means you're going to do probability of 20 plus 21 plus 22 plus 23, all the way to 60 now to go up, which is a lot of work. Or you say, okay, let's not do that. I learned my lesson, let's do the complement. But the complement is still 1 minus the probability of 0 and 1 and 2 and 3 all the way to 19. So it's still a lot of work on both sides. So it is doable, and of course with a little bit of technology, it's not impossible to do. But the big idea here is that, remember from 4.2, at the end of when we studied binomial distributions, we saw that the larger the n, the closer these distributions really look like being normally distributed. So if you put a normal curve along this one, it already looks kind of normal. Or this is almost perfect. If you, imagine like there's a normal here that goes probably better than that. Probably something like this. And I can't draw it. Okay, but the idea is that the more n, the bigger, the closer these are being to being normal. And remember, we also knew that the mean of these normal binomial distributions were, the mean was NP, where n is the number of trials and p the probability of success, and the standard deviation of these binomial distributions were the square root of NPQ. So this is exactly what you're going to be using for this red curve, the red normal curve that has the probability of success. The red curve is going to be the normal distribution has mean NP, which is the mean of the binomial, which is that tipping point, right? That's the value here. And the standard deviation is NPQ. Okay, so now it doesn't always work. We want this to be large samples. It also depends on the P and the Q. So what we want is, we really need NP, this is the immediate criteria, and one of those things that we're not going to tell you why, but we need the NP to be more than 5 and the NQ to be, at least 5, so 5 or more. If you have that, then you can go on and say, I can approximate my binomial distribution by a normal distribution with this mean and this standard deviation. Okay. Now there's something called the continuity correction, or correction for continuity, and this is the fact that when you're doing these normal distributions, these binomial distributions, you're looking at these these rectangles that look something like this. Okay, and then they start going down, and you're approximating that via a normal curve that does something like this. So pretend these numbers are, let me put some numbers here. Pretend this is like the center at 20, this is 21, this is 19, this is 18, and it's centered at the center of the rectangle because these are just the probabilities of these outcomes, and they're discrete, right? So it makes sense that they're at the center and that the width of these is 1, and they go like that, and you move them. So when you want to find the area, for example, for 20 probability that something is, let's say less than 20, less than or equal than 20, for example. Well, I would do with probabilities, with the sum of binomials, I would need to add the area of that blue one, the area of this rectangle area, right? With the red curve, if you do less than 20, if you say, okay, I'm going to do my normal approximation, I'm going to find a normal CDF starting from a negative number and ending at 20, that would technically be wrong. Sorry, here you put your mean and your standard deviation. Because less than 20, you would be starting here, right? You wouldn't include the rectangle at 20. And you won't include it because it says less than or equal to 20. So the problem here is that while the binomial was discrete, okay, the binomial was discrete, the normal is continuous, right? So this is what we're dealing right here, that the binomial distribution was a discrete and the red one is continuous. So how do you handle this? Well, if you want to include the 20, then on the normal curve, you really should not be doing 20. You should be doing 20.5. Why? Because that way you'll be including this rectangle, this area from here, and that's the area you want, right? So you're gonna have to move 0.5 to the left or to the right, depending on the situation. If it's less than, you have to move to the left. If it's less than or equal, you have to move to the right. If it's more than, you move to the left, and so on. So each problem would have to use your judgment to know which one you have to move. But and the probability is going to change slightly, not much in the end result, but it's something that had to be taken care of. So this is this example. A drug manufacturer claims that the drug cures a rare skin disease in 75% of the cases, and the claim is checked by testing the drug on 100 patients. So it means that n is 100. Let me write it down because then it's hard to keep track of what's happening. My probability of success is 75. So to do whatever the question is, if I'm going to do a normal approximation to a binomial, I need to check, is NP more than 5? Oh, it is, of course, because 100.75 is 75, so of course it is, right? How about NQ? Well, it is. NQ is going to be the 25, so it's going to work. Okay, so we can use a binomial approximation, so it'll be the normal approximation to binomial, so we're fine. Okay, now, find the probability that the claim will be rejected, assuming that the manufacturer's claim is true. So we're assuming that 75%, and you can test it to 100%. So 200 patients, sorry. If at least 70% are cured, then the claim will be accepted. When will it be rejected is the question. That means we want to find what's the probability, let me change this color and like it. We're going to find a probability that X is less than 70, right? Because it will be rejected if this is not true, and it will be accepted if it's at least 70. This includes the 70. At least 70 means 70 or more, and it will be rejected if it's less than 70. Okay, so I'm going to be doing normal CDF onto a normal curve that, to the left of, this is not going to be 70. Let me put it here, not going to fit my numbers. Let me write over here. Normal CDF to a negative number, 269.5. Right. Why? Because I want to do less than 70. I'm not including the 70. So it's this continuity correction that we're doing here. Okay. And then what is the mean on my normal curve? My mean is NP. So this is my mean. And my standard deviation is the square root of NPQ. So you can type this directly in your command, but let me write to find out what's standard deviation. It's nice to know what is standard deviation. So I'm going to type the square root. I'm doing my calculator over here, sorry. Let me get rid of this somewhere, okay. Clear. So second square root of n, which is 100, times 0.75 times 0.25, I get a 4.33. Okay, so then I get, now listen to this, normal CDF of a lower number, a negative number, upper 69.5, under the mean is 75, and standard deviation 4.33. And we get 0.102. Okay, so it's about 10% chance that the claim will be rejected. Something that sometimes bothers some students is I'm putting a negative number here. While it makes no sense that you have negative patients, and yeah, you're right. I mean, it doesn't make sense to put negative patients, but now when I'm writing this, all I'm doing is finding the area under the red normal curve, which goes on forever on the negative side. So if that bothers you when you want to put a 0 here, but that's the last number that makes sense, that's fine. My mean is 69.5. Standard deviation is 4.33, so you're moving tons of standard deviations to the left if you go to 0. But just be careful that sometimes it might happen that this doesn't, you still have to go to the negative side, okay? Even if further constant doesn't make sense. Once you get to the model, the red curve, the normal approximation, then you have to use the model, okay? It's not a big deal if you don't. Okay, let me do the last example. Credit card charges. A survey of U.S. adults found that 41% have encountered some fraudulent charges on their credit cards. And if randomly select 100 U.S. adults, find the probability that the number who have encountered fraudulent charges on the credit card is exactly 40, at least 40, or fewer than 40. So I put this on the purpose because the part A says exactly 40. This is not normal approximation. So for part A, you are still doing a binomial PDF. You're just finding one value, exactly 40. So binomial PDF of NPQ, where N is 100, you're selecting 100 adults. P is 0.41, and probably 6, and you're looking for 40. Okay, that's all number 1 is asking. So you do, let me do it again. So I go to second distributions, go to my binomial PDF. Number of trials is 100, probability of success is 0.41, X value is 40. I get a 0.79. 0.079, so about 8%, 796. Okay, now for at least 40, now it's when I would be doing 40 or 41 or 42 or 43 and add them all up together. So this is the one where I want to use a normal approximation, and I need to check two things. I need to check, is NP more than 5? Of course it is. Because N is 100, P is 41 again, so that's 41, right? Is NQ more than 5? Yes, it is, because Q is 59 times 100, it's 59. So, of course, it's more than 5. So we can use the binomial approximation. So, in fact, who is my mean? My mean, if you want to find it, well, it's NP. It's exactly 100 times 0.41, so it's my 41. Who is my standard deviation? It's the square root of NPQ. So it's the square root of NP, which is 0.41 already, right? So these two guys together were over here. And then times the Q, which is 0.59. So my standard deviation is, let me do it, second square root of N PQ. I get 4.91. 9183. Okay, so what I need to do for part B, I need to do normal CDF, so part B. Normal CDF under normal curve, at least 40. So I'm including, let me write down, I'm doing the probability that X is greater than or equal than 40, right? It says at least 40. That means I want to include the 40, so I'm going to the 40 to the right. So if you wanted to visually see what's going on, you want to do something like this. The 40 is right here. You want to include the 40, so you really have to go 0.5 to the left and include it, right? So I'm doing from 39.5 to a big number, okay? Under a normal curve that has mean 41 and has standard deviation 4.9183, okay? So normal CDF, second distributions, normal CDF of a 39.5, upper a big number, mean 41, standard deviation 4.9183, and I get 0.6198, or about 62%. I'm going to go with 6198. Okay. And part C, fewer than 40, well, that's going to be on the other side, right? So at least 40 was 40 or more. Fewer than 40 would be less than 40, so you can just do 1 minus what I just found. So 1 minus 0.6198 is 3802.